at the end of the lesson, the learner is able to represent real-life situation using logarithmic functions and solve problems involving logarithmic functions. So our lesson outline, logarithmic including common and natural logarithms. So application, we have Richter scale, decibels, and pH levels. So our definition. So let A, B, and C be positive real numbers such that B inequality 1. The logarithm of a with base B is denoted by log A with base B and is defined as C equals log with base B if and only if A equals B squared C. And a reminder, so in both the logarithmic and exponential forms, B is the base, and the exponential form, C is an exponent. This implies that the logarithm is actually an exponent. Hence, logarithmic and exponential functions are inverses. In the logarithmic form, log x with a base B, x cannot be negative. The value of log x with base B can be negative. So we have the two types of logarithms. So common logarithms are logarithms with base 10. Log x is a short notation for log x base 10. So kapag nakita natin tong log x, ibig sabihin ng base niyan ay automatic 10. Hindi nyo lang nakikita because it's a short notation for log x with a base 10. Our natural logarithms, so we have, kapag yung base natin, we can write in this ln x or y. So let's try this one. Rewrite the following exponential equations in logarithmic form whenever possible. So, ito yung mga answer ng mga pinakita ko na kaya na yung solve natin. So, kung magtataka kayo, and I cannot be written in logarithmic form because, so it's alright to have a negative exponent but not a negative base. So, hindi siya pwedeng ma-write in a logarithmic form. So here for our example to rewrite the following logarithmic equations in exponential form. So write logarithmic equation exponential form. So this is reverse kabaliktaran naman. So form logarithmic to exponential form. So first we have log m equals n. This is an example of common logarithm. Automatic our base. So an automatic our base is 10. So in B we have log 81 with a base 3 equals 4. So in logarithmic form, we have to write it 3 to the square root of 4 equals 81. So, ito yung mga answer in our problem and writing logarithmic equation in exponential form. Here we are going to find the value of the following logarithmic expressions. And in down, we have the answer of each question in this example number 3. So we have here another applications. Some of the most common applications in real life of logarithms are the Richter scale, sound intensity, and pH level. In 1935, Charles Richter proposed a logarithmic scale to measure the intensity of an earthquake. He defined that the magnitude of an earthquake as a function of its amplitude on a standard seismograph. The following formula produces the same result, but it is based on the energy released by an earthquake. So, with earthquake magnitude on a Richter scale, the magnitude R of an earthquake is given by R with a 2/3 log A with 10 to the square root of 4.40. Where E and joules is the energy released by the earthquake. The quantity 10 powered by 4.40 joules is the energy released by a very small reference earthquake. So the formula indicates that the magnitude of an earthquake is based on the logarithm of the ratio between the energy it released and the energy released by the reference earthquake. Example 4. Suppose that an earthquake released an approximately 10 to the power of 12 joules of energy. A. What is the magnitude on a Richter scale? B. How much more energy does this earthquake release than the reference earthquake? So in our solution, we have A. Since E equals 10 to the power of 12, then R equals 2 over 3 log A 10 over 4 when 10 to the power of 4.40 equals 10 to 2 to 3 log 10 to the power of 7.6. So since by the definition, log 7 to the power of 6 is the exponent by which 10 must be raised to obtain 10 to the power of 7.6 equals 7.6. Those R equals 2 over 3 to 7.6. So 5.1. So be this earthquake releases 10 to the 12 power of 12 over 10 to the power of 4.40 equals 10 to the power of 7.6 equals 3981017 times more energy than the reference earthquake. So sound intensity. In acoustic, the decibel dB level of sound is D equals 10 log 1 I1 over 10 to the power of 12. Whereas the sound intensity in watts or M to the power of 2. The quantity 10 to the power of negative 12 watts M to the power of 2 is the audible sound a human can hear. So in example 5, the decibel level of sound in a quiet office is 10 to the power negative 6 watts or M to the power of 2. A. What is the corresponding sound intensity decibels? And B. How much more intense is the sound than the less audible sounds a human can hear? So in our solution, so as we can see in A, D equals 10 log 10 to the power of negative 6 over 10 to the power of negative 12 equals 10 log 10 log 10 to the power of 6. Since by the definition, log 10 to the power of 6 is the exponent by which 10 must be raised to obtain. So 10 to the power of 6, then the log 10 to the power of 6 equals 6. So in those D equals 10 with 6 equals 10 decibels, 60 decibels. And B, the sound is 10 to the power of negative 6 over 10 to the power of negative 12 equals 10 to the power of 6 equals 1,000 times more intense than the less audible sound a human can hear. So, acidity in the pH scale to the 6. The pH level of a water-based solution is defined as pH equals log with H to the with the power, where H plus is the concentration of hydrogen ions in moles per liter. Solution where with a pH of 7 are defined neutral. Those with pH greater than 7 are acidic, and those with pH less than 7 are basic. So we have here example 6. A 1-liter solution contains 0.00001 moles of hydrogen ions. Find its pH level. So since there are 0.001 moles or hydrogen ions in 1 liter, then the concentration of hydrogen ion is 10 to the power of negative 5. It's the exponent by which 10 must be raised to obtain 10 to the power of negative 6. Then log 10 to the power of 6 equals to the power of negative 6 equals 5. This pH, so our answer is negative log 10 to the power of negative 5 equals to the negative 5 equals negative 5.